Hey, hello everyone. The next session which we are going to see is about CTS, clock tree synthesis. Okay, why they call it as heartbeat of digital circuits or digital designs, right? Because CTS is the one. For example, we are working on a synchronous clock designs, right? So CTS is the one which will help your flops to toggle and you go to the next stage. Okay, so that's why they call it as heartbeat of digital circuits. So once your clock is ticking, that's why your next stage data is read, data is next data is read. That is how that is why CTS is very important. Okay, now let us go and see what are the things we do at CTS. Okay, and how we do it. The importance and challenges in clock tree synthesis. Okay, the key challenge here, some of the key challenges in CTS is first thing is your latency, skew, and LDRC. Why they are very important? Because these three factors are the one which will determine the quality of your CTS. Okay, so what is latency? Latency is the arrival time from your source of the clock to your leaf pin or clock pin of your flop or a macro. Okay, that is a latency. And clock skew. Okay, clock skew we have generally they classify into two types. One is the local skew, other one is a global skew. Global skew means the difference between the arrival time of two flop is the global skew. Okay, but if the same difference between arrival time is calculated between two communicating flop, okay, which are there your which you check in your timing, right? This is called local skew. Okay, and the DRCs generally the logic DRCs we check with respect to the library. They call DRVs also, right? With respect to the library or within a given target, how much transition is accepted? That is what very simple terms we can put. Okay, and next thing is we will check us the timing. Okay, so timing right now timing is very critical when you come to designs which uses CCD. Why? Because it's not only the skew. Okay, it also depends upon how much the if you reduce the skew, right? Your setup and hold will be better. Okay, if your skew is high, then you have completed your placement, whatever timing you have closed may not hold good here. Okay, that's why it is important. And hold is very important here because skew directly affects the number of buffers you add it. And other one is power. Okay, so the clock network, right? Both your flops as well as your entire buffer tree synthesis which you have done toggles a lot because once the clock goes to 0 1 0 1 0 1 0 1. So now these circuits also toggles a lot. So there will be a switching power, there will be a short circuit power. Okay, so we need to see, okay, how the buffer, the selection of buffers and what layer you are going to route determines your power here. Okay, it is generally recommend to have small buffers than bigger buffers because small buffers gives you a lesser dynamic power. Okay, what are the other things? The other one is OCV, on-chip variation. This depends upon the divergence of the clock tree. Okay, for example, when two flops are talking to each other, if they are sitting together and they are connected to same buffer, now the divergence is very small. But if they are distance apart, right, because of your placement, then you will see buffer tree which are uncommon to both these flops. This will create more OCV effect. Okay. Next, let us see what are the methods and structures, different structures of clock tree synthesis. I have just put it here, H tree, X tree, fishbone, clock spines. Okay, let's look into what are they. First is H tree. Okay, so the name itself says the structure, right? You will see a H here. Okay, the source will be in the center of the search tree, and The clock signal is split and routed in the shape of H. Okay. Use case ideal for uniform sync distribution in both X and Y direction. It is commonly used in most of the large chips, okay, where frequency is a concern. The advantage is this is a balanced path length, almost zero skew, and it is very scalable, provides a very deterministic timing because the skew is very less. But the disadvantage is the wire length and power is very high for the structures. Okay, because of the wire length. For example, if you want to have multiple H trees, you will build this is the H tree, then you will have one more H tree here, one more H tree here. So when you do it, the congestion increases for the H tree. Okay, and it works best only when the sinks are uniformly distributed. For example, right, if you have lot of sinks distributed in this place, and you have very less sinks here. Okay, so even here you have to build one more H tree here. Okay, you cannot build only H tree here. Then you need to build H tree here, 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 because you need to balance it, right? So that's why when sinks are not distributed, your H tree length will be very high. Okay, next is the clock spine structure. You see, right, there is a spine here. From that spine, each flop is connected to that spine. Okay, this is the spine structure. This shape resembles to a straight line with the short branches going out. Okay, works well for chips where sinks are spread across in the main axis. If the sinks are there in this axis, right, then it will be very good. Okay. It is a simple routing, okay, low insertion delay if the sinks are aligned. Okay, so, but if the sinks are more not aligned, when the ID will increase. Okay, disadvantage, it may have higher skew if the sinks are uneven. Okay, sink distribution is uneven, and it is very less flexible. Okay, next is the fishbone structure. You see here, right? The fishbone. See, it is similar to clock spine, but the thing is, fishbone after it will be like a single, or you will have multiple parallel spines also. Then there will be a rib. Okay, so so that from the rib it is connected to all the sinks. Okay, the shape looks like a fish skeleton with central backbone and evenly spread ribs. Uh, Advantage, better skew control and good balancing delays. Okay, what is the disadvantage? It has also wire length is higher, like similar to whatever we saw in the clock spine, right? Here also uh, the wire length and power will be high. Okay, next is the X-tree structure. See, this X-tree is a type of structure, but mostly it is not used in the industry. I'll tell you why it is not used as well. But first, let's look into the architecture. The root is at the center here. Okay, unlike other trees, right? Here the root is here, and from here it is distributed everywhere. The shape symmetrical X patterns with equal path lengths from the root to sinks. Okay, clock distribution branches out diagonally in the shape of X. What is the use case? Designed for balanced clock distribution when sinks are spread diagonally, okay, across the quadrants of the chip, and useful in chips that need low clock skew and symmetric placement. Okay, these structures are good for better clock skew also. Advantage, you will see zero skew and highly symmetrical distribution, good for high frequency designs. Better delay balancing compared to fishbone or spine. Okay, what is the disadvantage? Not very routing friendly. Okay, that's why people don't go for it, because we cannot route in X fashion, the diagonal fashion, right? Whatever it is mentioned here, it is a little bit very complex to achieve that pattern, and higher wire length and power consumption, and less flexibility for irregular sync pins. Okay, if the pins are irregular, then there is no flexibility here. Okay, next is what are the clock networks, how it is organized, right? You will see a clock source. Okay, clock source may be a PLL, or if it is a block, you may have a block pin. From there the source is taken, and primary and secondary drivers. You see, even though you see it's like a line, but you will see the buffers are added here. Okay, repeaters are added here. Then local buffers. Local buffers after the sync, right? You can add some buffers. May not, if the fan out is high, may not be directly to the sync, but you can add some buffers. Leaf level cells and flops. Okay, leaf level cells are nothing but the flops are your memory or macros. Okay. Best practices in industry, industry trends in CTS. What are the things we do? Okay, before CTS is built, okay, in the pre-CTS optimization, we will have a better clock gating. Clock gating is used to control power. So whenever because with the enable signal, whenever that particular set of clock pins, right, is not switching, you can just disable that particular clock so that there won't be a switching, and switching power will be saved. And during CTS, we will insert buffer and inverters. You can also do shielding. Once the net is routed, you can shield those nets, okay, with VDD or VSS to prevent crosstalk and noise. And generally, they use dedicated routing layers for clock so that your SA will be reduced. Next is the post CTS refinement. During refinement, you can fix DRC violations also. And once the clock tree is built, it'll do some iterative skew to balance the skew. Uh, and the DRC fixing right now in flows like a concurrent optimization, data clock and data optimization. You will see the DRC or DRV fixings also done in parallel. And clock power analysis we do, optimization we do, and also we will check the SI signal integrity verification after extraction. Okay. Next is deliverables. Generally, right now the industry trend after CTS, people move to optimization and routing. But if you want, you can take it to, if you want to take it to sign off, you can write out a def and spef and give it to the sign off. Okay. Nowadays, modern CTS EDA tools, right? They have advanced features like concurrent clock and power optimization. Okay, useful skew exploitation. Okay, you can use useful skew and close the design. Machine learning. Okay, machine learning is another emerging topic in the physical design. Okay, so this is just an I can say summary of what we do in clock tree synthesis. Okay, it needs a lot of expertise in clock tree for closing the designs, because as we see all these parameters achieving it, right, it's not very easy there, okay, in a complex circuit. Okay. So that's it I have. Okay, thank you for your time here. Follow me in Facebook. Okay, thank you everyone. Bye.